So we're going to continue our discussion on sequences, and we're going to be talking about arithmetic sequences specifically. Some of you might have already seen or spoken about arithmetic sequences in previous math courses. It's a very common sequence, sections 4.2 and 4.3. Let's get started. So what is an arithmetic sequence? An arithmetic sequence is it's a sequence. So if you recall from yesterday, a sequence is a set of numbers in a specific order, but it's a sequence where the difference between consecutive terms is always equal. So that basically means there's a common difference, which is our second vocabulary term for today. And common difference, you'll see in a moment, is pretty simple, and the definition is just difference, and we normally write it as D of an arithmetic sequence. So let me move this up here and show you some examples of something that would be considered an arithmetic sequence. So here we have a sequence, right? It's a consecutive set of numbers, ... It'll keep going forever and ever. Now if you notice what's going on between terms, well, common difference, so that means difference is going to be common, and difference means subtraction. So the difference between the two terms, well, between 14 and 7, what's the difference? 7. 14, let me do this with a different color. 7. 14 minus 7 is 7. Between 21 and 14, what's the difference? Again, 7. Between 28 and 21, 7. So is there a common difference? Yes, the common difference is 7. So this would be an arithmetic sequence. And an even easier way to figure out whether something is an arithmetic sequence is by doing it the other way around, by seeing if there's a pattern, by seeing if we're adding the same number every single time. So instead of thinking of it as a difference, we're using addition instead. And that's the case. We're always adding the same number, adding 7, which means from this term here to the previous term, that means we're subtracting by 7. So there is a common difference here of 7. The common difference is a 7. Let's do another one. So is this an arithmetic sequence? Well, is there a common difference? What's going on here? Let me use blue. So from 1 to 6, what am I doing? Well, I am subtracting by 5. I'm sorry. I'm not subtracting by 5. I am subtracting by -5. Okay, from 1 to 6, I am subtracting by -5. From negative, which that means we're adding 5, right? Because from 1 to 6 we add 5. A negative and a negative would be a positive, but we're trying to write this in terms of a difference, so that's why I subtracted by -5. From -4 to 1, we are subtracting by -5. From -9 and -4, we are subtracting by -5. So there is a common difference, and that common difference is -5. Or we could go about this by seeing if there's a pattern. Well, from 6 to 1, what am I doing? I am adding -5. From 1 to -4, I am adding -5. And this might be a bit easier to think about if we do it this way. Just take a look at if there's a pattern. If we're adding the same numbers, we're adding -5. I don't want to say pattern because I'm going to show you one in a moment that has a pattern but wouldn't be an arithmetic sequence. We have to be adding the same number in order for this to be an arithmetic sequence, and it is. We're always adding -5, so this would be an arithmetic sequence with a common difference of -5. Let's do one more example. So instead of doing let's do it both ways. So here, what are we doing from 4 to 2? We're subtracting by 2. What are we doing from 8 to 4? We're subtracting by 4. What are we doing from 14 to 8? We're subtracting by 6. So there's a pattern, right? We're subtracting by consecutive even integers, but it's not common. We're not subtracting by the same integer. Okay, it has to be the same integer. So would this be an arithmetic sequence? No, it would not. We don't have a common difference. There would be no common difference. So this would not be an arithmetic sequence. Now, I don't want you to think that this equals x. I just meant to show that there is no common difference. Let's move on. So we can write our arithmetic sequences in two ways, either explicitly or recursively. Let's take a look at this. You could read the scenario on your own if you wish, but would this be an arithmetic sequence? Let's do this just by taking a look and see if there's a pattern. Is there a pattern? Yes, we're adding 500 every single time. So this is an arithmetic sequence, and the common difference would be what? 500. Now, how would we write a recursive rule for this, or how would we write an explicit rule for this? Let's start with recursive. Well, recursive, we learned this yesterday, or today, depending on when you're watching this video. With a recursive, remember we always have an initial starting point, that f of 1. So with this problem, what would our f of 1 be? Well, our f of 1 is going to be 200. 2,000. I'm sorry. And now we need to come up with a general recursive rule for this entire table, for this entire set of data. Okay. Well, what's going on between terms? We are adding by 500. We are adding by 500. So if we're trying to get to the second term, f of 2, what would we need to do to our previous term? Add 500. All right, and we would get 2,500, which is f of 2. But we're trying to come up with a general recursive rule. So what would the general recursive rule be? Well, it would be f of n equals, remember and recall how to write previous term using function notations. It would be f of n minus 1, and that just means previous term. And what are we doing with each previous term? We are adding 500. And that's it. That would be your recursive rule. Adding 500 every single time to our previous term. How would we write an explicit rule with this? Well, this right here, we're adding 500, but this is a rate. We're adding 500 every time we change our input value. We're adding 500. Okay, so this is a rate. That means we're going to be multiplying. We're multiplying 500 times every single time we change our input value. However many times we change it. It doesn't have to be specific. We want a general rule, so we're going to use a variable. 500 times n. Now, here's the thing, though. If we use this rule right here, this wouldn't work, right? Because 500 times 1 would not be 2,000. So, in this case, you could think of this as two ways. We could either just recognize that we're going to have to add a constant to this in order to make this true, which would be plus 1,500, right? Or you could go back to, well, what would f of 0 be? What would our 0 term be? And if we do that, our 0 term would be 1,500. Our initial term would be 1,500, right? Because if we're adding 500 every time to go from term to term as we're increasing, if we're decreasing, we would have to subtract by 500, right? So our 0 term would be 1,500, and that right there would give you your initial term, your initial constant, which is 1,500, and obviously we're writing this in function notation, so that would be f of n equals 500n plus 1,500. But if you don't want to worry about finding that 0 term, then just find that common difference, which in this case was 500, right? Know that you're going to have to multiply 500 by your domain, by your n, and then just take your first term and subtract it by that common difference, which 2,000 minus 500 is just 1,500. That's a constant. That's our first term. That's what we're adding. Okay. I hope that makes sense, but we're going to do more examples in class tomorrow, so if it doesn't make sense, we'll talk about it a bit more. In general, these are the general rules that we could use to find recursive rules and explicit rules. Okay, so and we're going to use these in just a moment. So in general, if we're trying to write a recursive rule, if we're given the first term, which we have to be given the first term in order to write a recursive rule, and in order to work with recursive rules, if we're given the first term, then all you would need to do is put f of n minus 1, which means previous term, and just add it by a common difference. And this is obviously going to be for anything after your first initial term. With explicit, I don't really like the way they have it here, but you could use this if it's easier for you. But I like the way that we just did it a moment ago. So with explicit, all you would need to do is write, well, f of n equals your very first term, which is f of 0, right? That's f of 1 really isn't your first. Your very first term would be f of 0 plus just your common difference, plus d, okay? You could also use this, and it would also work, whatever's easier for you. Or you could just get your very first term like we did with our previous example, and just add the common difference times, I'm sorry, I forgot this, times your position, times n, okay? Your common difference times n. So here we have a sequence, and we are asked to write, what are they asking us to write? A recursive and explicit. So let's first stick with recursive, and we're going to use this this general recursive rule here. So with recursive, first we're going to have to find our common difference. So you could do it with subtraction, or you could just try to find the pattern. I'm just going to try to find the pattern. It looks like every time we are adding by -12, right? We are adding by -12. Adding by -12. So our common difference is going to be -12. So with our general recursive rule, if we use this formula right here, it would be f of n equals your previous term, so f of n minus 1, and then plus your common difference, which in this case our common difference is -12, so we could just write -12. If you take a look at that, that'll work, because f of 1 we know is 100, right? Well, what would f of 2 be? If we're using this rule right here, that means it would have to be our previous term minus 12, which is 88. It does work out. So that would be our general rule for our recursive. It would be f of n minus 1 minus 12. So with explicit, we'll do it both ways. We'll use this, and then we'll do it the other way that I did it with. So I said, well, we could just do f of n equals f of 0 plus dn, okay? But you could do whatever way you want to do it, whatever way is easier for you. Let's first start with the way that your book shows you. So if we use this, well, remember this 100 would be my first position, this 88 would be my second position, this 76 would be our third position, and we learned this today or yesterday, depending on when you're watching this video. So these are just my positions, and these are the terms on that in that position. So in position 1, my term would be 100. So if we're using the general explicit rule given to you by the book, it would be f of n equals f of 1. What's f of 1? 100. Plus d times n minus 1. And that's it. Oh, wait, I'm sorry. That's not it. D, we actually have to actually put in what the common difference is. I'm sorry about that. So your common difference would be we got that from our previous recursive example, where your common difference would be -12. So this would actually be 100 minus 12 and minus 1, right? And that's if you're using what the book gives you. Now, if you do it the way that I did it, well, we would first need to find f of 0. So if we're subtracting by 12 from term to term, we'd have to add by 12 in order to get f of 0. So f of 0 would actually be 112. That would be f of 0. Okay, so if you're doing it that way, then you're using this right over here, then your explicit rule would be f of n equals our f of 0, which f of 0 is 112, plus, well, not plus, because our common difference is -12, so it would be minus 12n. And if you went ahead and used the distributive property and simplified this equation here, or this function here, you would see that you would end up with this. Okay, you would get the same thing, except this is already simplified, and we could just leave that like that. Okay, so now we're going to go ahead and write an explicit rule for the sequence given to us by this graph, and then we are going to use that rule to find the height when the stack is 7 boxes tall. So let's just go ahead and construct a little table here, just so that we could kind of organize all of our inputs, outputs, organize all of our positions in our terms. So our inputs are positions. So at position 1, and position 1, at our when our input is 1, what is our output? Well, when our x is 1, what is our y? It would be 34. So that would be your first term. So at position 2, it would be 51. At position 3, it would be 68. At position 4, it would be 85. Is this an arithmetic sequence? Absolutely. We're doing the same thing every time. We have a common difference. We're adding 17 every single time we have that pattern. So our common difference is going to be 17. Now, how would we write an explicit rule for this? Well, if we use the kind of shortcut, general shortcut that I gave you a moment ago, remember to write an explicit rule. It's just f of n equals f of 0 plus the common difference times your position times your input times n. So first we would need to figure out what f of 0 is. Well, if we're adding 17 every time, that means if we're going backwards, we would have to subtract by 17. So f of 0 would be 17, right? So if we're writing a general explicit rule for this sequence, it would be f of n equals f of 0, which is 17, plus our common difference, which is 17, times n. Okay? Now, we would need to use this to figure out, well, how many, or how tall is the stack when we have 7 boxes. So, it isn't explicit. So luckily, because it isn't explicit, we could just plug this in. If this was recursive, we would have to find every single previous term. But it's explicit, so we could just go ahead and plug in this information. So if we're looking for f of 7, we would just plug in 7. It would be 17 plus 17 times 7. And that would be 17 plus 119, which would be 136. So f of 7 would be 136. And that's it. So we'll work on this a bit more tomorrow. And if you need any additional help, just come to tutoring. All right, I will see you tomorrow. Have a great day.